Okay, so this is a bond enthalpy question, and it says the conversion of ozone to diatomic oxygen is represented by the equation above. Based on the data in the table above, what is the approximate average bond enthalpy for the oxygen to oxygen bonds in ozone? Okay, that's interesting. That's really interesting. Okay, okay. So give that a shot, right? Like, that's really interesting. Bond enthalpy for the oxygen to oxygen bonds in ozone. Oh, that's really interesting. All right, so that's going to take some thought. I'm going to have to think about it too. So let's give this 3 minutes, okay? Hey Siri, set timer for 3 minutes.
Okay, 3 minutes and counting.
It's a hard question. Okay, Jacob. That's tough. Yeah, those are less stable. Okay, so okay. I'm still thinking through this one too, Antonio. So Antonio has an answer. Let's take another minute or two. I just want to think through this a little bit more. It's a good question. Okay. So my okay, good. My recording from yesterday is ready. I'll upload it to YouTube after today. today's session. Okay. So, okay, so you've got two of those, you got those. So, okay, let's call that. Okay. All right. So I'm going to try to walk through the solution that I'm coming up with because I need to be able to write on something to like think through this properly. So, all right. So you've got three O2s, right? Three O2s. And for me, that's three O double bonds approximately. It's not actually a double bond, which is why this problem throws me for a loop. It's actually a radical triplet, but you can approximate it as a double bond, I guess.
Mhm.
So let's go with that. All right. So that means 3 times 500 equals 1500. Okay. So that's the total bond enthalpy of the three O2s, right? And we always do reactants minus products on this one. So reactants minus products equals negative 300. Okay, so that means reactants equals 1200, right? So how many bonds do we have in the reactants? Well, we have two um, O3s, right? Which means you've got O with some kind of bond to another O with some kind of funky bond, right? So there's a resonance structure here
Mhm.
to another O, right? And you got this times two, so then you've got another O, 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 O. So you got four of these things, right? Four of these things. Okay, so let's call this x, right? So 4x equals 1200. So x equals 300. So I'm going with that. I'm going with C. And I really had to draw that whole thing out. There were just too many numbers and too many darn things going on for me to be able to do that any other way. Like I needed to draw everything out and really see what I was dealing with before I was going to get comfortable. So I would go with C. What did you guys get? I don't actually know what the answer is. What did you guys get?
I was
I got
thinking
C
C
as
as well.
You're thinking C as well? What were
Yeah.
you thinking, Jacob?
I was thinking C.
Okay. Kate, what about you?
Ditto. I got C.
Okay. Rainisha? You can just shoot me a text or a chat. And then who else? Symphony. Symphony, what did you get?
Well, I didn't understand, so.
Okay. Rainisha says she got C also. Very good. Okay. Yeah, this was not straightforward. Okay, let's see what the answer is. Good. Okay. So same thing. Yeah. Yeah, that's a little brutal because I don't like the way that the College Board is treating this. That isn't really fair. Like they're treating resonance structures as static things, and they're treating the OO bond as a true double bond, which it isn't. So I think this was actually a badly designed question, but you're not going to see it on the AP test. And going through all of these steps is still okay. So if you just sort of accept the approximations that we have to make to do this, you're okay. So let's go with this being okay. All right, I'll erase. Sorry, does anybody need any further explanation? Symphony, are you good on this one now?
Yeah.
Okay, I'm gonna go ahead and erase the board. All right, so 17. We're gonna get through all these pretty quickly. Okay, the combustion of methane proceeds according to this chemical equation. The table above provides the average bond enthalpy for selected bonds. The calculated enthalpy change for the reaction is negative 802 kilojoules per mole. Which of the following provides a mathematical procedure to estimate the bond enthalpy per mole of oxygen? Oh, I see. That's fun. So you don't have O2, but you have the other ones. You have all the other bonds. So CH, and you have CO, and then you have the CO double bond, and then you have the H2O. So you have the OH single bond. Oh, that's interesting. Okay, yeah, give yourself some time to really think through this. Okay, this is like one of those kind of like long, winding mathematical deals. So take 4 minutes. Okay, this is stuff you know, but you have to sort of think about it in a different context. So, hey Siri, set timer for 4 minutes.
Your timer is set for 4 minutes.
Somebody already have an answer? Okay, cool. You got it, Caden.
Dr. J, we're allowed to use calculators on all of this test, right? There's no
Yeah, you are.
calculator?
You're allowed. That's the whole thing. That's why I got you those calculators. So I have those calculators at home with me. Like Caden, I could literally drop one off at your house.
Okay.
Anybody else who needs one, we'll just have to figure it out.
Is the TI-84 going to be allowed on the test or no?
Oh yeah, for sure. You can use
Oh,
that one instead.
Perfect.
Mhm.
Yeah, I got this one from calc class, so I'll just hang on to this.
Good idea. Make sure you've got fresh batteries for it, just in case they conk out on you at the wrong time.
Yeah.
Okay, so normally you do. Okay, guys, so I haven't solved this one yet, so I'm gonna hold off on responding to chats until I've solved this one, and then I'll respond. Okay, so yeah, Kate and I got the same answer as you.
Okay.
It just took me a while to think through the whole thing. The hard part for me is that on a problem like this, I really want to be able to write down my answer. But if I start writing on my whiteboard here, yeah, Symphony, I got the same thing, and Antonio, I got the same thing. Okay, good job. Okay, so uh, Jacob and who else? Jacob and Ray, was it Ray Nisha? Jacob and Ray Nisha. How are you guys doing?
Pretty good. I'm still working through it. It's really long.
Okay. Yeah. Okay. Ray Nisha, did you find the answer? You're still working too? Okay. Take a couple more minutes. Take like 2 more minutes. This is a problem you want to give yourself time to work through. Hey, Siri, set timer for 2 minutes.
A timer is already running.
Not anymore.
It's not running. Hey, Siri, set timer for 2 minutes.
Your timer is set for 2 minutes.
Yeah, just give yourself a little more time. And then I'll put the answer up. And I need to get better about pausing the recording, so I'll pause the recording right now. Nice. Okay, so here's how this works. So you start out with, where's the thing? Okay. All right, so you've got, why am I on C? I don't understand that. Okay. So you've got this reaction going on here, right? And normally the way that you do this is you do products minus reactants, or sorry, reactants minus products for this one equals, for bond enthalpy, equals delta H, okay? When you've got for bond enthalpies. So for bond enthalpies, okay? So reactants minus products. Okay, so what do you get? So if you go reactants minus products equals delta H, then you get, like the reactants are, you've got, okay, 414, but you've got 4 of those bonds, okay? Four carbon-oxygen bonds because it's CH4. And you've got 2 of these oxygen-oxygen double bonds, which you don't know. So that one plus 2x, we don't know what that is, right? Minus now, because we're going to subtract the product enthalpy, bond enthalpies. So minus, you've got CO2, so that's 2 CO double bonds. So you've got minus 2 times 799, and you've got also minus 2 H2O. So you actually got 4 OH bonds. So 4 times 464, okay, equals negative 802. And of course, that's kilojoules. Okay, and you really want to isolate your 2x, right? So you get 2x equals negative 802 minus, okay, 4 times 414, right? Plus 2 times 799 plus 4 times 464. Okay, and then you get x equals 1/2 all of this, which is this thing, A. Okay, any questions? Okay, did I make any mistakes? All right, let's double check. Yeah, that's A. Okay, that's that. Any questions about that? Jacob, does that make sense now?
Yes.
Okay, good. Rainisha, does that make sense? She'll text me or let me know in the chat. Okay, so I'm gonna go ahead and erase this guy in perfect, Rainisha. In 3, 2, 1. All right. And then chat. Okay, and then number 18. Okay, the formation of hydrogen chloride gas is represented by the chemical equation H2 gas plus Cl2 gas yields 2HCl gas. Based on the bond enthalpy data in the table above, what is the approximate enthalpy change for the reaction total? Okay, so let's go ahead and take, let's take 4 minutes to do this. I feel like that's a good idea. So, okay, so I'm gonna pause the recording. Okay, so here's how this problem works. So we've got reactants minus products gives us delta H. And we start on the, so I'll back up actually a little bit. So
I also want to say it yields 185, not negative.
here are our reactants, right? So H2 and H2 has an HH bond enthalpy of breaking, right, of 436. So it takes 436 kilojoules to break that bond. And then we've got to add an additional 243 kilojoules to break the Cl-Cl bond. But when the HCl bonds form, we get 2 of them, right? And we're going to actually release 2 times 432 kilojoules per mole to produce those bonds. So when you do the math on that bottom line there, what you get is all of it equaling negative 185 kilojoules per mole. But that's a weird unit. Just call it 185 kilojoules. I don't know why they're doing that mole reaction thing. That's not a unit with which I'm familiar. Okay. So negative 145 kilojoules is your total reaction enthalpy. Okay. Given that the reaction is presented appropriately with all molar coefficients in their at their lowest common multiples or whatnot. Okay. So that's it. So that's how that problem works. And we have no further questions. So I'll go ahead and erase the board and we'll move to our next question. Number 19. We're doing great. Okay. So calcium carbonate decomposes according to this balanced equation. Based on the standard enthalpies of formation provided in the table above, what is the approximate enthalpy change of the reaction? Aha, okay. These are enthalpies of formation. So these are enthalpies of formation for individual chemicals, right? So this is how much we get when we have enthalpy of formation. So in this case, what we do is we subtract reactants from products, okay? So we do products minus reactants equals delta H when we're dealing with enthalpy of formation, okay? When we're dealing with enthalpy of formation. That's not good notation. So when we're dealing with delta H. We're dealing with delta H of F on this side, okay? So that's the scoop. So go ahead and give this one a shot. We'll do like 3 minutes for this guy, okay? I'll pause the recording here. Okay. So in this reaction, what we have is CaCO3 turns into calcium oxide and CO2. Okay, great. And so the heats of formation of calcium oxide and carbon dioxide are negative 390 kilojoules per mole for carbon dioxide, and then negative 640 kilojoules per mole for calcium oxide. Okay. And then the heat of formation of calcium carbonate is negative 1210 kilojoules per mole. And so we have to remember, for these problems, we subtract the products from the reactants to get our overall change in bond enthalpy, which makes sense because enthalpies of formation are, the heat required to form these things, just like a reaction forms something. So we should have products minus reactants. So,
Okay.
All right. So we do so products minus reactants, so negative 1030, okay? That's the sum of our products. When you add the negative 640 and the negative 390, you get negative 1030, minus negative 1210. So that's ultimately an addition. So you're actually going to add 1210 to negative 1030. And when you do that, you end up with positive 180, okay? And our unit is kilojoules. And we'll double check that that's correct. And there was much rejoicing. Okay. So any questions?
So yeah, so conceptually the way I'm picturing this is that when the bonds form, so heat of formation means that when the bonds form, this is the heat, this is the energy change that happens. So since it's negative, this heat is released, right?
Yes.
Okay. That's okay. So then to break that is the opposite. It needs that much heat for those bonds to be broken, and then to form
Yeah.
those other ones, the heat released. Okay, so that's why
Yeah.
it's products minus reactant.
Yeah. So like for when you're dealing with bond enthalpies, you do reactants minus products. Why?
Right.
Because the bond enthalpies are enthalpies of required to break bonds. But in a chemical reaction, we're doing the opposite thing. We're actually forming the bonds at the end. So
Right.
we have to, because we're doing this opposite thing over the course of the reaction going forward, we have to do a sign flip. So we have to do reactants minus products in that case. But in the case of enthalpies of formation, when we use enthalpies of formation, those are forming, right? Just like our products are forming during the reaction. So we can subtract reactants from products in that case. Okay, it's a normal delta from final value minus initial value.
Okay.
Okay, yeah. And if that whole thing doesn't make sense to you, just remember, okay, products minus reactants for heats of formation, and then reactants minus products for heats or bond enthalpies. Okay, all right. And so I'm going to go ahead and clear the board, and then we're going to go to number 20. Okay, so the information above, what is delta H for the reaction? SO2 gas plus 1/2 O2 gas yields SO3 gas. Okay, that's fun. And you're given heats of formation here. Oh, this is fun. Okay, so everybody's gonna have a good time. This is pretty straightforward. We're gonna take like 2 minutes to do this one, okay? And I'll pause the recording right now. What? Why? Okay, so for this situation, all we have to do is we have to say to ourselves, we're forming SO3 and we're breaking SO2. So negative 395.2 kilojoules are released per mole of SO3. So we get this, but we're breaking up SO2. So negative 296.1 kilojoules are going to be what is it? Not negative. So are going to have to be reversed. So we're going to have to input that many kilojoules. So it's this. So minus negative 296.1 kilojoules. And so that equals negative 99.1 kilojoules. Okay. So B. All right. So any questions about that one, scholars? Yeah, this is pretty familiar to us now. Okay. So I'm going to go ahead and erase the board in 3, 2, 1. And then let's take a look at number 21. All right. Okay, so natural gas consists primarily of CH4, which is combusted according to the following chemical equation. Based on the standard enthalpies of formation in the table above, which of the following expressions gives the approximate enthalpy change for the reaction? Okay, so go ahead and let's take 2 minutes to knock this out. I think we can do this in 2 minutes. Okay, so hey Siri, set timer for 2 minutes. Hey Siri, set timer for 2 minutes.
Okay, 2 minutes and counting.
Okay, so for those of us who are, so everybody crushed this one. So for those of us who are following along by the video, here's how this one works. So we've got these two, right, minus this guy, and well, or these two, right? Remember O2, that's an element. So elements always have heats of formation of 0. So I just ignore them when I go through, and that's just by convention. They have heats of formation of 0. So you can, anything that's purely elemental, you can ignore, at least as long as it's like the common form of the element. Like certain allotropes, like ozone, might have a different might have an actual heat of formation, but it's going to be pretty negligible actually. Okay, so what you've got is CO2, which is negative 390, right? So it's always products minus reactants equals delta H, and then negative 390 plus negative 240, right? Minus, okay, negative 75. All right, and that's just C. Okay, that's just C. Oh, and I forgot the coefficient. So negative 240. You got to multiply this guy times 2. Okay, so that's where this guy comes from. I forgot that guy. And I should have seen him because he's right there. Okay. All right. So that's how that one works. And I'm going to clear the board in 3, 2, 1. Okay. So problem, man, we are crushing it. Problem 22. Okay. Oh, these are fun. Okay, so figuring out how to combine the equations. Okay, so given the equations and the values of delta H for the combustion of ethane and the combustion of graphite, which of the following additional information is needed to determine the delta H values of the overall reaction? Graphite plus H2, which of the following piece of additional information is needed? And you got to form plus H2. Okay. gives C2H6. Okay, that's really interesting. All right, so you're trying to figure out which additional reaction would allow you, with the other two presented on top, to go ahead and determine the enthalpy of this reaction. Okay, so that's what we're trying to figure out. I'm going to erase that so it doesn't mar the board, but we're trying to figure that out. Uh-oh. I clicked like the wrong thing. Uh-oh. Okay, where's AP Classroom? There it is. Okay, so I'm going to erase this guy. All right, so go ahead and try to figure out which of these reactions would help you get here, okay? And you'll take, let's take 3 minutes to do that. Hey Siri, set timer for 3 minutes.
Okay, 3 minutes and counting.
Okay, so here's how I solved this one, right? I said to myself, okay, if I'm gonna get down here, then everything except for graphite, H2, and ethane must cancel out, right? Everything else has got to cancel out. So like, take a look at A, right? There's this diamond. If I include this diamond somewhere, I'm never going to be able to cancel it out. Like I'm never going to be able, like it's going to be on one side and it would wind up in the final equation, right? Because I'm either going to use the forward reaction for diamond turning into graphite, or I'm going to use the reverse reaction. I can't use them both because that wouldn't make any sense. And so if I do that, right, my diamond never cancels out. So A can't be correct, right? And then it's the same thing over here with part B. If I introduce ethene, right, my ethene's never going to cancel out. There's no ethene in either of these reactions, right? There's no ethene there. There's no ethene there. So like no ethene. So B's wrong because ethene doesn't make sense. C's okay because H2 and O2 and H2O are present in both of these guys up above, right? So that makes sense. So they're that's good to go. But then I don't see what I'm getting out of H2O turning into H2O, right? Because there's no H2 there. So I've got to have H2 somewhere in my third reaction. So D is out because it doesn't have any H2. So the only possible answer is C. Okay. Any questions, scholars? Okay. All right. So let's take a look at the next question here. Let's just double check. Very good. Okay. And then, all right. So let's take a look at number 23. Okay. Two reactions presented, and then we get an overall reaction. The enthalpy of the overall reaction represented above can be determined by adding the enthalpies of reactions 1 and 2. Which of the following could be reaction 2? Okay, so very similar to the last question we did. Very good. All right, so let's go ahead and pause the recording, and you'll have 2 minutes for this problem. Okay, so for this one, the correct answer ends up being C. Okay, and why is it C? Because if you add this in here, you get 2NO plus O2 yields 2NO2. Okay, then that's going to give you, right? You initially didn't have your 2NO2, so the 2NO2 get added, right? And you initially didn't have your 2NO, so the 2NO get added, right? And here's the fun thing: you had 2O3 turning into 2 O2s. So you have to cancel out one of these O2s on the right side, and this allows you to do that. Okay, that cancels, and then you get a 2 there. Okay, and so that's how that works. Antonio, does that work now?
Yeah.
Okay, so that's how that answer is correct. Okay, and none of the other answer choices will do that for you. And we'll double check just to make sure. The book agrees with us. The book agrees with us. Okay, so I'm going to go ahead and erase the board in 3, 2, 1. And just really quickly, any questions about that one, scholars?
No.
Okay, very good. All right, so let's go ahead and look at 24. This is our last I think this is going to be our last problem for the day, guys. I just don't think there's any reason for us to get started on the free response questions today. We've only got we'll only have about 20 minutes left after this. So I think it'd be a good time to just let those go until tomorrow. And then tomorrow we'll do free response, and then we'll review all of these again. And then on Thursday, we'll do some Albert problems and or some textbook problems. And then we'll kind of talk strategy at some point too. Okay, does that sound reasonable?
All right.
Cool. Okay. All right, so the table above provides the values for the standard enthalpy change for two chemical reactions. A student needs to calculate the enthalpy change for the reaction to nitric acid, liquid goes to 2N2O5 gas plus H2O liquid, okay? Under standard conditions using Hess's law. All right. In addition to the values given in the table, what other information will the student need to perform the calculation? All right, so go ahead and give this a shot. Let's take 2 minutes. So, hey Siri, set timer for 2 minutes. Hey Siri, set timer for 2 minutes.
Okay. Your timer is set for 2 minutes.
We'll just... Okay, so we crushed this. You guys did an awesome job. And what you noticed immediately was that between these two equations, right? This chemical is not present. So you have no information whatsoever on the heat of formation of N2O5. So B is absolutely the correct answer there. Okay, we can't proceed without that information. So very good job. Okay, and the College Board of course agrees. All right, let me kill the timer. Okay. Yeah, okay guys. So we've done a really, really good job today. All right, we just knocked out all the rest of those review problems. And so I think we're all set. Does anybody have any last questions or anything that he or she would like me to go over? Or like if you've been working on something else and you want me to stay on for a little bit longer to go over those problems with you, that'd be fine too. But otherwise, what I'm gonna do is I'm gonna go ahead and pause. Any quick questions, first of all?
Not really.
No, I think I got this.
Perfect. Then I'm going to stop the recording.